This video is going to cover three problems that you'll run across in the homework leading up to test 3. So let's look at all three of those, starting with a test of the mean. Normally, our test of the mean is going to provide us with sample information, including sample size, in this case 12, sample mean, in this case 27.9, and sample standard deviation, in this case 6.5. And it would also give us a claim test at the 0.05 significance level that the mean age buyers of the new smartphone is less than 30. So the mean is less than 30 is the claim. And we would take that claim, mu less than 30, and set up our hypotheses. Again, H0 is always equal, and the alternate hypothesis relationship is going to be the same as the claim, since the claim did not have the condition of equality in it. Once we've done that, we would typically use the calculator hypothesis test, the t-test, under stat test, to find the test statistic and the p-value. So we would go to the calculator, and we would enter the information. Hang on a second here, stat, right arrow to tests, and number 2, t-test. We would make sure stats is highlighted, and we would enter the alternate hypothesis relationship 30, which is the assumed value for mu, the mean of the sample, 27.9, the standard deviation of the sample, 6.5, and the sample size, 12. And then we would identify the relationship in the alternate hypothesis that the mean is less than the 30, okay? Then we would go down to calculate, say, rather than, we could choose to draw and see the p-value sketch, but let's just use calculate here. And we get a test statistic of negative 1.119 to 3 decimal places, and a p-value 0.1435 to 4 decimal places. So that's how we would normally do that. But if we were to be given the same basic problem, but without the test statistics, let's go back and look at the problem. We have, instead of the test statistics, all we have is a sample values. In order to do this, without the statistics, we couldn't go to the t-test necessarily. We would have to know what x bar is, what s is, and what the sample size is. We could go put this into the calculator, which we're going to have to do anyway. Put these into a list, call it L1, and we would find, using 1-bar stats on L1, we would find these statistics that we had over in this first problem, rounded to these values. But if we are doing the hypothesis test on the calculator, that gives us an option to have the calculator do all of that for us. We just have to make sure the data is in a list, and then we run the 1-bar stats, I'm sorry, not 1-bar stats, but the t-test, and tell it what the list is. So let's go back to the calculator. Okay, and we see that when we run the test, stat, right arrow to tests, and number 2, that we have an option of data or stats. Stats we would use if we knew what x bar is, what sx is, or the sample standard deviation is, and the sample size. but we don't in this case. So we're going to go arrow over to data and hit enter to make sure that is selected. And notice that instead of asking for X bar and S and N, it asks for the list. And it will calculate those statistics from that list and then run the test or do the calculations for the test statistic and the p-value. But you still have to put in the assumed value of mu from H0, and you still have to select the correct relationship in the alternate hypothesis. So if we leave this at L1 and run the test, we will see that we get those values, negative 1 point, well, not quite those values, because I think we got we got the mean test statistic, the test statistic was negative 1.119 and 0.1435 when we just use the statistics. When we use 27.9 for X bar and 6.5 for SX, but when the calculator does this, when it finds X bar and SX, it keeps all of the decimal places. It doesn't round and uses these unrounded values to find the test statistics. So this is more accurate when it uses the original data instead of rounded statistics. So we get t equals negative 1.108 and the p-value is 0.1458. So if we use those, let's go back to the document. When we use those, we're still going to get the same results, okay? We're still going to see that the p-value is greater than alpha, and therefore we'll fail to reject H0 and make the same, have the same conclusion. But so if you do not have the sample statistics, but you do have the sample values, then you're going to select data instead of stats when you run the t-test, and you will have to put the data from the problem into a list. So let's look at the second problem, and this one is a test of standard deviation. If we run do a test of standard deviation, we don't have a calculator hypothesis test to tell us what the test statistic is and what the p-value is. So for this problem, we're given in a sample, we're given the sample standard deviation and the sample size, which we're going to need to compute the test statistic. And we're given the claim, which is that the standard deviation is less than 10.5, from which we come up with the alternate, the null and the alternate. The null is 10.5, equals 10.5, always equal. And since the claim was sigma less than 10.5, the alternate hypothesis will be the same. Sigma or standard deviation less than 10.5 was the claim, didn't have equality in it, therefore this is the same as the claim. We take that information, the assumed value is going to be from H0 10.5, and the statistics, the sample standard deviation and the sample size from the problem. We put those into the formula for chi-squared and get a test statistic of 4.215. Then we would have to go use the chi-squared CDF function. Since the mean of this, with the sample size of 12, the mean is 11, and 4.215 is less than 11, which makes it to the left of 11. We're going to find the area underneath the chi-squared curve from 0 up to 4.215. So the chi-squared CDF will have a lower bound of 0 and an upper bound of 4.215. And we have to specify the degrees of freedom, and we get a p-value of 0.0368. And I invite you to go through this process on your own to verify that the numbers I put in here are correct. And we compare the p-value, of course, to alpha. 0.0368 is less than the significance level of 0.05. Therefore, we're going to reject H0. And since the claim did not include equality and we're rejecting, that means we're supporting the claim that sigma is less than 0.15 or 10.5. And I've also put in here the critical value, which we would have to go to table A4 to find. Since it's a left-tailed test, we would, the area to the right is 0.95 because all of alpha is in the tail to the left of the critical value. And look in the, that's in the one tail 0.95 column, and look in the 11 row, which is the degrees of freedom, to get that critical value. And we see that it is farther from the test statistic, which was 4.215, is farther away from the mean, farther to the left than the critical value, causing us to reject H0. Now, suppose we have a problem then where we do not have the sample standard deviation, and we need that sample standard deviation in order to calculate the test statistic. Well, we would have to take the information from the sample, put it in a list, and run one bar stats to get the sample standard deviation. We would round it to 1 decimal place, and we would end up with 6.5. And then we could, and we know that there's 12 sample values, and so the degrees of freedom, of course, is 11. We would be able to find the test statistic, and once we've got that, we would be able to find the p-value. So if you do not have the sample standard deviation in a test of standard deviation, but you do have the sample values, you're going to have to put those values in a list and run one bar stats to get the sample standard deviation, and then proceed from there just as you did without, or when you did have the information, the statistics. And the third problem is where this is not, we're still going to have the statistics here, but we have an additional question being asked in here. So let's basically take the original problem and run quickly through it, and then we'll see what this additional question is. Okay, so we've got a table of statistics from 2 different samples from 2 populations, and the claim is given to us as test that there is no difference between the mean heights. Well, when we have no difference, that means they are the same, they are equal. So we're testing that the first mean is equal to the second mean. The first sample, not sample, but population mean is equal to the second population mean. And we get, from that, we have our null hypothesis where it's always equal. So the claim did say equal, mu1 equals mu2. So the alternate hypothesis is going to have a relationship that is the complement of equality, which is not equal. And so it's a 2-tailed test. We put our data into the 2-samp t-test, which is how we're going to run all of these two sample tests. And let's go look at the 2-sample t-test, 2-samp t-test in the calculator. Let me quit out of here. We're going to go to stat, right arrow to tests, and we want number 4 in this case, 2-samp t-test. And let's go back and set up stats here, because we do have the statistics. And so now we need to run this with the set of statistics. So let's put the data in here. Okay, the first mean is 38.7. And the second mean, or first standard deviation is 2.7. The first sample size is 25. The second mean is 36.6. Second standard deviation is 4.1. And second sample size is 25 as well. The claim was not equal, so we put the cursor over that and hit enter to make sure that is selected. And you'll notice in this test, it did not ask for the assumed value of the parameter. The parameter, remember, is mu1 minus mu2. And if we look at the null hypothesis, it specifically says mu1 equals mu2. They're the same, which means the difference is 0. And in all of our problems, using two samples here, the assumed value of mu1 minus mu2 is equal to 0. So since it's always 0, it doesn't have to ask for that value. It assumes that it's going to be 0. And then we go down to calculate, and we hit enter. And we get our test statistic is is 2.254. And our p-value is 0.0182. And double check and make sure we had the right inputs here. 38.7, 2.7. Made a mistake here. Let's go back and quickly correct that to get the proper output here. Stat, tests, number 4. And the data that I put in there is still there. And so this is 2.7. 25, 36.6, 4.1, and 25. Everything else is still correct. And we hit enter. And now 2.139 is the correct test statistic, and 0.0384 is the correct p-value. Okay, so that's how we run the 2SAM t-test. We take the p-value then and compare it to alpha. And let's stop sharing here and go back to the document. And since the p-value is less than alpha, we're going to reject H0. And since the claim included equality, we're going to conclude there is sufficient evidence to warrant rejection of the claim that the two population means are equal. Now we go back to the additional question in the test of difference between means. That is, what happens, does a confidence interval support the claim, support our decision and our statement of conclusion from using the 2SAM t-test, the p-value approach? Well, there are actually 3 ways that we can conduct a hypothesis test. Test using the p-value approach, test using the critical value approach, and we can also use something called the confidence interval approach, in which case we basically build a confidence interval, and then let's say alpha is 0.05, then the confidence level is 1 minus that, which is 95% in this case. Then if the assumed value of the parameter from H0 is inside the interval, then we will fail to reject H0. So if the left boundary of the confidence interval is negative and the right boundary of the confidence interval is positive, we will fail to reject. If both of them are the same sign, if the upper bound, lower bound and upper bound are negative, that means we're 95% confident that the true parameter is negative instead of 0. And if they're both positive, then we're 95% confident that the positive interval contains the true parameter, in which case, in those two cases, 0 is not in there. So we will reject the claim, or we'll reject the H0, which says that it is 0. So let's take a peek at how we would do this, since we have not done confidence intervals before for anything but proportions. There is a test on the calculator that allows us to do this, and that is the 2samp t int. So let's clear this out, go to stat, right arrow to tests, and let's go down to, notice these are ints now. 2samp t int means interval, rather than 2samp t test being the hypothesis test. And it's going to calculate the interval for us. Then our work that has to be done is to determine if the assumed parameter is in that interval. If we have a lower bound that is negative and an upper bound that is positive, that means 0 is in that interval. And since we're 95% confident that that interval contains a true value, since 0 is in there, we cannot reject it. Okay, so let's run the 2samp t int. I still have the data in here because I just ran 2samp t test, and it's still got the same statistics. All I need to do is make sure I've got the correct confidence level, which is 1 minus alpha. Since alpha is 0.05, this is 0.95. And this is for a two-tailed test, by the way. We had 1 minus alpha is what we put in there for a two-tailed test. And we go down to calculate, and we get a confidence interval that goes from 0.118 up to 4.082, and those are both positive. If they're both positive, that means that it does not contain 0, which means we are going to reject the null hypothesis that the difference is 0. Okay, so that would be our decision. And does that support what we had done when we used the p-value approach? Let's take a quick peek and see. We rejected H0 using the p-value approach. We would have rejected the H0 using the critical value approach, and we would have rejected H0 using the confidence interval approach. Okay, so you will reject H0 in a 2samp t test. If you used a critical value, the confidence interval, you will reject H0 if both values are positive, or the upper bound and lower bound are positive, or both negative. You'll reject H0. Okay, and fail to reject if the left bound is negative and the upper bound is positive. The p-value, critical value, and confidence interval approach decisions will always agree. Okay, so those are the 3 kinds of problems that you'll run into. So let's stop sharing. And this is going to be the last video supporting test 3. So I wish you good luck on test 3.